A power series has the following form, where the coefficients and a are real numbers, and here we say the power series expansion is centered around a. Now for the special case where x is equal to 0, the power series has the following form, which is expanded as follows. And for the further special case, where all the coefficients are 1, then this is written as follows. So this form of the power series is a geometric series where the ratio is x and the constant is 1. So therefore the geometric series has the following sum of 1 on 1 minus x. And here we have several terms in the series, so the more terms we introduce, the better that the series approximates the exact sum of the geometric series. And note that the geometric series converges when the absolute value of the ratio is less than 1. So the interval of convergence is from -1 to 1. Given the following power series, it can converge in one of the following ways. So number 1 is the power series can converge over an interval. So effectively, the interval of convergence for this power series centered on x equals a is a minus r to a plus r, where r is called the radius of convergence. So basically just add a to all these terms. Then outside this interval of convergence, the power series diverges, and at the endpoints of the interval, or at a minus r and a plus r, the power series may converge or diverge. So we need to test those endpoints separately. Now the second way a power series can converge is for all values of x. So in this case, the radius of convergence is infinite, and the interval of convergence is from -infinity to infinity. And the third way a power series can converge is at a single point. So in this case, the radius of convergence is equal to 0, and the power series converges at a particular x value and diverges for all other x values. And to determine how the power series converges, we use the ratio test. Well, we take the absolute value because x minus a can be negative. So we have the ratio of the next term in the power series to the current term in the series. And this ratio test is going to tell us which of these convergence conditions that the power series satisfies. To determine the radius of convergence for a power series, we use the ratio test. So we take the limit as n approaches infinity of the absolute value of the next term in the series to the current term in the series. And we take the absolute value because this expression can be negative. So therefore what we end up with is the limit as n approaches infinity of the absolute value of the following expression. And factoring out the absolute value of x minus a, we obtain the following expression. And by the ratio test, this must be less than 1 for the power series to converge. So this is going to give us the radius of convergence and the open interval of convergence, which looks something like this for a power series centered on x equals a. So recall the convergence conditions. we can have convergence over an interval at a single point, or for all values of x from minus infinity to infinity. And we'll see that in a few examples. If a power series has a radius of convergence greater than 0, then the series defines the following function. On the open interval, from a minus the radius of convergence to a plus the radius of convergence. And f of x has derivatives of all orders which converge inside this interval. And we'll see that this condition means that the power series is the Taylor series of the function, to which it converges over the open interval. Now if we differentiate the series term by term, we obtain the following expression. And differentiating again, we obtain the following expression. And note when n equals 0, this expression is 0, so we can sum from n equals 1. And when n equals 0 and n equals 1, the first two terms are 0, so we can sum from 2. And the radius of convergence of the series defining these derivatives is the same as the radius of convergence of the original power series. And I encourage you to show that using the ratio test. If a function is defined by a power series centered on x equals a, which converges on the open interval from a minus r to a plus r, where the radius of convergence is greater than 0, then the following power series converges, and the integral of the function also converges on this interval. And the radius of convergence of this series is the same as the radius of convergence as the original power series. So here we've integrated the terms in the series using the power rule for integration. And I encourage you to show that using the ratio test applied on this series and then applied on this series. And term by term integration can be used to identify a function represented by a power series or obtain a power series representation of a function. So they're the typical uses of this theorem. Given the following power series expansion about x equals 0 with constant coefficients of 1 for all n, so in other words, this power series can be expanded as follows. We're asked to find the radius and interval of convergence and describe the convergence using the curves below. Well, this is a geometric series with the ratio of x between the terms, so this only converges if the absolute value of the ratio is less than 1. So therefore this gives us an interval of convergence between minus 1 and 1. And the radius of convergence is half of the interval of convergence, so that would be 1. And now according to these curves, when we use one term, we get a horizontal line, and as we increase the number of terms that we use in a series, we get a better and better approximation to this sum. So for n equals 1 we get a linear approximation, for n equals 2 we get a parabolic approximation, and if we use terms in those series up to n equals 10, that gets a much better approximation to the sum. So you can see that the series is going to converge to the exact sum. Let's find the radius and interval of convergence for the following series. And we recognize this is a power series because we can write it as follows. And now we check for absolute convergence using the ratio test. So we take the absolute value of the ratio of the next term in the series to the current term in the series. And we take the absolute value because x can be negative, and the ratio test applies only if this ratio is positive. And now doing a bit of algebra, and given that n is positive, and the first term evaluates to x, so we can take the absolute value of x outside the limit. And with these factorials, all terms cancel except n plus 1 in the denominator. So this can be written as follows. And therefore the limit evaluates to 0. So by the ratio test, rho is always less than 1. So that means the series converges for all values of x. So effectively, the radius of convergence is infinity, and the interval of convergence is minus infinity to infinity. Let's find the radius and interval of convergence for the following power series. So again, we check for absolute convergence using the ratio test. So we take the ratio of the next term in the series to the current term in the series. And we check for absolute convergence because x can be negative. So because n is positive, and x to the n plus 1 on x to the n evaluates to x, we can take the absolute value of x outside the limit and take the limit of the ratio of the factorials. So with these factorials, only n plus 2 is not going to cancel, and all the other terms are going to cancel. So therefore this limit is unbounded, and recall that for the ratio test, rho must be less than 1 for the series to converge. So therefore rho is less than 1 only for x equals 0. So for x equals 0, the series converges, and when x is not 0, the series diverges. So therefore the series converges only at a specific point, and therefore the radius of convergence is 0. Let's find the radius and interval of convergence for the following power series. And again, checking for absolute convergence using the ratio test. So taking the ratio of the next term in the series to the current term in the series. And doing a bit of algebra, and because n is positive, we can take the absolute value of x outside the limit. And therefore the limit evaluates to 1. So this series converges when the absolute value of x is less than 1. Or this can be written as minus 1 less than x less than 1. So therefore the radius of convergence is half the interval of convergence. And now we need to check the individual endpoints of the interval. So for x equals minus 1, we just substitute x equals minus 1 in that series. And we recognize that this is an alternating harmonic series, so we know this converges. So therefore the series converges at x equals negative 1. And now if we substitute x equals 1 in that series, well, 1 to the power of n is always 1. So therefore this is a harmonic series, and we know it diverges. And therefore the interval of convergence is minus 1 inclusive to 1, where the interval is open. Let's determine the radius and interval of convergence for the following power series. So again, using the ratio test, we take the limit of the ratio of the next term to the current term in the series. And then doing a bit of algebra and taking the absolute value, we obtain the following limit. So for the series to converge, we have 2 by the absolute value of x must be less than 1 by the ratio test. And therefore, we obtain minus a half less than x less than a half. So the radius of convergence is 1/2 of the interval of convergence. So now we test the endpoints of the interval. So we substitute minus a half into the series. So that will be minus 2 by minus a half to the n, or 1 to the n on root n plus 1. And I'll leave it for you to verify that this diverges. And testing the second endpoint, so we'll just substitute 1/2 into the original power series. So that'll be minus 1 to the n on root n plus 1. And I'll leave it for you to also test if this series converges. And then you'll obtain the interval of convergence and post your answer in the comments. Determine the radius and interval of convergence for the following power series. So again, we test for absolute convergence using the ratio test. And then doing a bit of algebra. And the absolute value is going to cancel out the -1. And the absolute value of x squared is just x squared. So we can take that out of the limit. And then the limit's going to evaluate to 1. So for the series to converge, x squared must be less than 1. Which is the same thing as minus 1 less than x less than 1. So the radius of convergence is half of the interval of convergence. And now we test the endpoints. So for x equals minus 1, we substitute back in the original power series. And therefore you get minus 1 to the power of 3n plus 1 in the numerator. So this is an alternating series, which satisfies the 3 conditions of the alternating series test. So the series converges at minus 1. And similarly, we substitute 1 into the original power series to test that endpoint of the interval. So 1 to the 2n plus 1 is 1. So this is another alternating series that converges. So verify that yourself, and you'll find that the interval of convergence is minus 1 to 1 inclusive. Let's find a power series, radius and interval of convergence for the first and second derivative of the following function. So we recognize that this is a sum of a geometric series with a equals 1 and a ratio of x. So we can write the function as follows. And now differentiating this function, we obtain the following series. And note that we take n equals 1 because this constant drops out. And differentiating again, we obtain a series for the second derivative. So we just use the power rule. And differentiating term by term, and now we can test this derivative for absolute convergence using the ratio test. Which gives the following result. And the limit evaluates to 1, so the derivative converges when the absolute value of x is less than 1. And therefore, the radius of convergence is 1. And the interval of convergence is open from minus 1 to 1. And if you follow the same step for the second derivative, you should obtain the same result. Let's find the analytical function given by the following series. So if we expand this series, and differentiate each term, so we recognize the derivative is a geometric series with a equals 1 and a ratio of minus x squared between the terms. So therefore we get an analytical function for this geometric series of a over 1 minus the ratio squared. And now if you separate the variables and integrate both sides, well, what we get is the function is equal to the arctan of x plus the constant of integration. And if we recognize that f of 0 is equal to 0, because x appears in all these terms, so what you get is the constant of integration is also 0. And if you did your convergence checks on this series, which we've done previously, so you'll see this series converges on the closed interval from -1 to 1. And this is clear from the plots here. So as we increase the number of terms in a series, we get a better and better approximation to the arctan function, but only inside the interval of convergence from -1 to 1. So as we can see, the approximations to the exact function get worse outside the interval of convergence.